Imagine a world where everything marches to its own beat. Clocks drift, hearts falter, and fireflies blink randomly. Yet, this isn't our reality. Instead, we observe an astonishing phenomenon: synchronization. It's the hidden force that brings order to chaos, from the microscopic to the cosmic. This isn't just about things moving together, it's about independent entities, initially out of sync, spontaneously aligning their rhythms. It's a fundamental principle of nature, often overlooked, yet profoundly impactful. Its secret lies in the subtle interplay of coupling and feedback. The story of synchronization often begins with Christian Huygens in 1665. He observed two pendulum clocks, hanging from a common beam, mysteriously falling into perfect anti-phase synchronization. This was not by design, but an emergent property of their interaction. Huygens called it sympathy. He had stumbled upon the first documented instance of self-organization through coupling. This simple observation laid the groundwork for understanding complex systems across disciplines. From these humble pendulums, the concept expands. Planets orbit the sun in synchronized dance. Moons become tidally locked with their planets, always showing the same face. These celestial ballets are governed by gravitational coupling, a powerful synchronizing force. At its core, synchronization is a problem of coupled oscillators. An oscillator is anything that exhibits periodic behavior, like a swinging pendulum or a beating heart. When these oscillators interact, they can influence each other's phase and frequency. The secret is often found in the concept of phase locking. If the interaction is strong enough and the natural frequencies are close, the oscillators will adjust until their phases become fixed relative to each other. They lock into a common rhythm. This phenomenon can be described mathematically using models like the Kuramoto model. It demonstrates how a large population of weakly coupled oscillators can spontaneously synchronize. Even with diverse natural frequencies, a collective rhythm can emerge. The strength of coupling is critical. Too weak, and they remain independent. Too strong, and they might enter chaotic states. There's a sweet spot where order emerges from the collective. Nature abounds with examples of biological synchronization. Consider the mesmerizing spectacle of thousands of fireflies flashing in unison across a swamp. Each insect has its own internal rhythm, yet they coordinate their light signals. This collective display is not led by a single conductor. Instead, it arises from local interactions. Each firefly adjusts its flash based on the flashes of its neighbors, leading to a stunning, emergent synchrony. Our own bodies are masterpieces of synchronization. Billions of neurons in the brain fire in coordinated patterns, enabling thought and perception. The rhythmic beating of our heart is a synchronized contraction of countless cardiac muscle cells. Disruptions to this biological harmony can have severe consequences. Epilepsy, for instance, involves abnormal, hypersynchronous neuronal activity in the brain. Understanding synchronization is key to understanding health and disease. Beyond biology, synchronization manifests in human behavior. Audiences spontaneously clap in unison after a performance. People walking together often unconsciously synchronize their footsteps. These are examples of social synchronization. Even seemingly chaotic systems can exhibit synchronized behavior. Lasers, for example, rely on the synchronized emission of photons. Chemical reactions can oscillate in perfect rhythm, creating mesmerizing patterns. The secret here is often a shared environment or a feedback loop. The sound of clapping, the visual cue of walking, or the shared medium in a chemical reaction provides the coupling mechanism. However, synchronization isn't always beneficial. In power grids, unsynchronized generators can lead to blackouts. In complex networks, unwanted synchronization can propagate failures rapidly. Engineers harness the power of synchronization for countless applications. Global positioning systems, or GPS, rely on the incredibly precise synchronization of atomic clocks on satellites and receivers on Earth. Without this, accurate positioning would be impossible. Modern communication networks, from cellular to the internet, depend on synchronized data transmission. Timing signals ensure that information packets arrive and are processed in the correct order, preventing data corruption. In the realm of quantum computing, synchronizing quantum states is a monumental challenge and a critical step towards building powerful new machines. Controlling coherence is paramount. From the microscopic precision of microchips to the vast scale of power grids, Understanding and controlling synchronization is fundamental to technological advancement. It allows us to build robust, efficient, and reliable systems. The study of synchronization continues to reveal deeper secrets about the universe. Researchers are exploring its role in everything from the origins of life to the dynamics of financial markets. New insights into complex networks are showing how synchronization can emerge in unexpected places, and how it can be controlled or disrupted. This has implications for everything from treating neurological disorders to designing resilient infrastructure. The surprising secret of synchronization is its universality. It's a fundamental principle that bridges physics, biology, engineering, and social sciences. It reminds us that even seemingly independent elements are often part of a grand, interconnected rhythm. This pervasive phenomenon, from the smallest particles to the largest galaxies, underscores a profound truth. The universe is not just a collection of isolated parts, but a symphony of interconnected rhythms, constantly seeking coherence.